Okay, Chemistry 111, this is chapter 2, which deals with atoms, molecules, and ions. If you've never studied chemistry before, you might not have heard of ions, but you probably have heard of atoms and molecules before. And atoms are the smallest indivisible or the smallest forms of matter that can exist that retain a specific identity. So if we think about the periodic table of elements, all those elements on there represent specific atoms. So a carbon atom or a hydrogen atom or a nitrogen atom. And if we put atoms together, we can make molecules. So let's say we take two hydrogen atoms and an oxygen atom and we put them together, we can make what's called H2O, which is a molecule. And if you're wondering what an an ion is nothing more than an atom or a molecule that has a charge. So an ion can have either a positive or a minus charge. Now, something else I want to say about atoms is, what are atoms made of? Now, atoms are the smallest form of matter that retain specific properties, but atoms can be divided up into three different particles, three different what we call subatomic particles. They are made up of electrons, they are made up of protons, and they are made up of neutrons. So three subatomic particles make up atoms. Electrons have a negative charge. Their negative charge, and electrons reside on the periphery of an atom, whereas protons and neutrons exist on the inside of the atom, in the center of the atom, in something called the nucleus. So protons and neutrons are found inside the nucleus. I don't know how to write that without messing this up, but nucleus, protons and neutrons. Protons have a positive charge, and neutrons have no charge. Something else that's interesting is, if you look at the size and the mass of an atom, you'll see that most of the space of the atom is taken up by an electron, and the nucleus actually takes up very little space of an atom. In fact, if you compare it to something that we could understand, if you had like a football stadium, like maybe Coors Field or something, and you put a marble in the middle of that, the marble would represent the size of the nucleus, whereas the entire stadium would represent the size of the atom. Something else that's interesting is that protons and neutrons are much heavier than electrons. Protons and neutrons have masses that are very close, and they both weigh around 2,000 times more than an electron. So even though electrons are really small, they still make up most of the atom, and the nucleus makes up a very small portion of the atom, even though most of the mass comes from the nucleus. Well, if we go all the way back into history and we talk about the atom, it would start with a philosopher named Democritus. And what he said is, let's say you have a piece of matter. Okay, let's say you have, I don't know, it could be anything, a block of wood, let's say, or a piece of wood. And what would happen if you cut that piece, or cut that wood in half, and then you cut it in half again, and then you took this piece, and then you cut that in half, and then you cut it in half again, you took that, and you cut that in half, and you kept cutting in half, and cutting and cutting and cutting until you get to the smallest particle that couldn't be divided anymore. He called that particle atomos. But a long time later, way after the Greek philosophers had all been gone, an English school teacher named John Dalton came along and formulated a precise definition of indivisible building blocks that are called atoms. And Dalton's atomic theory is represented by these 4 points here. The first one is that elements are composed of these little particles that we call atoms, that are made up of electrons, protons, and neutrons. Atoms of a given element are all identical, having the same size, they all weigh the same, they have the same mass, same chemical properties. The atoms of one element, however, are different from the atoms of another element. The second part of this second point makes total sense. Atoms of carbon are different than atoms of oxygen. Atoms of oxygen are different than atoms of nitrogen. However, all atoms of nitrogen, or all atoms of carbon, or all atoms of oxygen are not identical. So we see that there's a little bit of a hole in the first part of the second point. However, this theory was developed in 1808. That's a long time ago, so we'll give him some credit. The next point is that compounds are composed of atoms of more than one element. In any compound, the ratio of the numbers of atoms of any two elements is present is either an integer or a simple fraction. So basically, when we make a compound, we take more than one element and we put them together and we make something new, but the elements are always present in whole number ratios or simple ratios. Let me give an example. Some of you have probably heard of carbon dioxide. Carbon dioxide is CO2, one carbon and two oxygens. And you might have also heard of carbon monoxide, which is CO. Now you notice that the ratio of carbon to oxygen in CO2 is 1 to 2. For every 2 oxygens, there's 1 carbon. It's a simple whole number ratio. And you see the same thing for carbon monoxide. We have a ratio of 1 to 1. There's no such thing as, C 1.5 and O 1.8. It doesn't exist. When atoms combine to make compounds, they're always present in whole number ratios or something very simple. Next is a chemical reaction involves the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. So basically, when we do a chemical reaction, we're not going to destroy anything. Okay, we never destroy anything. Now it might not be intuitive for some students. The example I always use is, let's say you burn a piece of wood. You pick up this big heavy piece of wood and you burn it. Where did it go? You feel like, hey, I've destroyed all the mass. Like it's gone. It's just gone. I don't know where it went, but now the ashes don't weigh hardly anything. Well, the answer is this: if you could tally up and if you could collect all the gases that were produced from burning the log and all the ash that was produced, it would weigh the exact same amount as the original log. Okay, you cannot destroy matter when you do a chemical reaction. If we continue on in talking about Dalton's atomic theory, we look at what's called the law of multiple proportions. And that is, if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in ratios of small whole numbers. Now this goes right back to that example that I just gave you, that if we combine carbon and oxygen, we can make these two different compounds, carbon monoxide and carbon dioxide. But the bottom line is that when the elements combine, even though they can make two different compounds, completely different, that the ratios of the compounds are going to be small whole numbers. Okay, so small whole numbers. Let's move on from there. Let's talk about the law of conservation of mass, which is related to Dalton's the fourth point of Dalton's theory, which is we're not going to destroy matter and we're not going to create matter in a chemical reaction. This is an example of a chemical reaction. We have 16x plus 18y. It's just a theoretical reaction. But the bottom line is that we're not destroying anything and we're not creating anything when we do a chemical reaction. If you're thinking, well, Mr. Dion, you are creating something. You're creating a new compound. Yes, what I'm saying is we're not creating any new matter. If you look at all the elements of, or all the atoms of element X, we have 16 of them. Look what happens in our product. If you add up all these gray spheres here, which represent X, you can see there's 16 of them. The formula for this compound is X2Y, and we have a total of 8 of them. 8 times 2 gives me 16, so I haven't destroyed any of the element X. The same thing applies to Y. We started with 8 of the element Y, and if you add up all these red spheres, you have 8 there as well. So again, we conserve our mass, we conserve our matter. We don't destroy atoms, we don't create atoms when we do a chemical reaction. Now, if you're getting way ahead of me, you might think, well, what about nuclear chemistry, Mr. Dion? You make new atoms there. That's something different. That's something that you study in general chemistry too, and we're not really concerned with that. And anyhow, we're not concerned with that. I'm going to skip over, and that doesn't mean it's not included on the second or on the first exam, but I'm going to skip over the history of the atom. So the cathode ray tube, Millikan's oil drop experiment, where he determined the mass of an electron, the types of radioactivity, Thomson model, which is what we call the plum pudding model of the atom, Rutherford's experiment. Again, it's important that you know this. I went over it in the videos that are posted to my YouTube channel. Rutherford's model of the atom, Chadwick's experiment. Yeah. So maybe we could start right around here, okay? And get back to our subatomic particles. So that, again, I want to repeat myself so you understand. It doesn't mean that those slides aren't important, but just in the interest of time, because of the snow day, I'm going to skip ahead to the properties of subatomic particles because that will be tested, I would say, more than the history of the atom. You still have to know about the history of the atom, but again, I go over that in a lot of detail in my lecture videos that I posted to D2L. So let's skip ahead here to the properties of those subatomic particles that I talked about on the first slide of chapter 2. The electron, the proton, and the neutron. If you remember what I told you earlier on, I said that the mass of a proton and a neutron is about 2,000 times less than that of an electron. In fact, it's around 1,840 times less, to be exact. If you take this number and you divide it by this number, you're going to find that the mass of protons and neutrons and electrons are all really small masses in grams, right? But you see that an electron weighs a lot less. Again, around 2,000 or 1,840 times less. Now, something else I told you is that an electron has a negative charge. I told you that a proton has a positive charge. Now, those charges can be measured in units called coulombs. I'm not going to stress about the charge units a ton, but you need to know that they have equal and opposite charges, a proton and an electron, and you need to know that a neutron has no charge. So take-home message is the difference in the mass between an electron and a proton and a neutron, which is summarized down here. And you need to know about the charge of an electron and a proton and a neutron. And with that knowledge, you can do quite a bit. Well, let's skip ahead to what's called atomic number, mass number, and what are called isotopes. Atomic number, which we represent with a capital letter Z, represents the number of protons, in a nucleus. Number of protons in a nucleus. Okay, and I told you that the nucleus is at the center of our atom. The mass number, however, A, uppercase A, represents the number of protons and number of neutrons in our nucleus. So another way of writing that would be to say the mass number is equal to the atomic number plus the number of neutrons. If you have an isotope, this is when you have atoms of the same element, but they have different number of neutrons. Now, if you're kind of confused or you're not following me 100%, let me explain it to you a little bit more. Okay? An atomic number governs the identity of an element. So gives, we could put here, gives element, or gives atom, let's do that, gives atom its identity. Whenever you try to do something quickly, it always ends up happening more slowly, huh? From here on out in this class, I recommend that everybody has a periodic table with them at all times. Okay, you should always have a periodic table with you in chemistry class. If you look at your periodic table, if you look at the first element, element number 1, it's hydrogen. The number 1 is the atomic number. It means there's 1 proton in the nucleus of a hydrogen atom. If you look at element number 14, let's say, it says Si, that represents silicon. 14 means that in the nucleus of silicon, there are 14 protons. So again, atomic number governs the identity of an element. The number of protons, or atomic number, is what governs the identity of an element. The number of neutrons doesn't affect an element's identity. It will, however, affect its mass because neutrons have the same mass as a proton. Now, getting back to isotopes, isotopes are atoms of the same element but have different numbers of neutrons. So we can summarize what we know. X, that represents the symbol of an element, like carbon, C, hydrogen, H, lithium, Li, sodium, Na. We looked at that in our first lecture. Up here we have the mass number, and down here we have the atomic number. If you look at these 3 elements right here, we have H, and just ignore these letters for now. You see that we have H with a 1, H with a 2, and H with a 3. Well, the H represents hydrogen, but the way that these 3 hydrogen atoms differ is that they're 3 different isotopes. How do I know that? If you look at their atomic number, the atomic number is the same for all of them. That means that each one of these three, they all have one proton in the nucleus. I told you that the number of protons governs the identity of an element. But up here is the mass number. The mass number is the sum of the number of protons and the number of neutrons. Could anybody tell me how many neutrons are in this isotope that I have circled in red? And it's not a trick question. Exactly, there'd be one neutron, because 1 plus 1 will give you 2. So that means that in this isotope of hydrogen, there is 1 plus 1 to give you 2. There's already one proton, so that means there must be one neutron. In this isotope, there must be 2 neutrons, right? Now, the way you describe these is the first one, you would call it hydrogen 1. The second one, you would call it hydrogen 2. And the last one, you would call it hydrogen 3. That's how you would actually name those 3 isotopes. Now, you're probably wondering why I crossed out the D and the T. I did it because I didn't want you to get confused. But instead of calling hydrogen 2, sometimes we call it deuterium. And sometimes we call hydrogen 3, we call it tritium. It actually has its own name, and we give them their own symbols. And if you're like, why are they so special? I don't know, they're just used a lot. So we give them their own names. Could anybody tell me what U stands for? Did anybody read through the entire periodic table and see what U stands for? Which element is U? Yeah, Anthony's got it. It's uranium, right? That means we have 2 isotopes of uranium represented here. We have uranium 235, and we have uranium 238. How many protons are in the nucleus of uranium 238 and 235? Who could tell me how many protons in the nucleus of each of these? 92, exactly. The answer is 92. Okay? Because the atomic number represents the number of protons. Now in uranium 235, I'll use P to represent number of protons. I have 92 protons. How many neutrons must there be? 235 minus 92. So if I take 235 and I subtract 92, I get 143 neutrons. Could anybody tell me how many electrons there would be in uranium 235? Does anybody have an inkling about that? There'd be 92. Now, if you're wondering how did people know that there'd be 92? The reason is because there's no charge on this uranium 235. If there's no charge, that means the amount of positive charge and the amount of negative charge, have to balance each other out. So there has to be an equal number of protons and electrons. We could do the same exercise over here for uranium 238. There are 92 protons. The number of neutrons is 146. And the number of electrons is 92. Same thing, same rationale. Well, if you look at the isotopes of hydrogen, we have hydrogen 1, we have deuterium, which we represent with a D, or tritium, right? All this slide is trying to show you is the difference in their nuclei being the plural of nucleus. The nucleus of hydrogen 1 has 1 proton. The nucleus of deuterium has 1 proton and 1 neutron. And the nucleus of hydrogen 3 or tritium has 1 proton and 2 neutrons. So those are the differences. But again, and I'm repeating this for probably the 100th time tonight, what governs the identity of hydrogen? The number of protons in the nucleus. Nothing more. With all that in mind, we'll try a couple of practice problems here on this slide, and we're going to have to move on from there and look at the periodic table in some more detail. Question 2.1 says, give the number of protons, neutrons, and electrons in the following species of protons, neutrons, and electrons. If I have sodium 20, you'll look at the periodic table and you'll see that sodium is the 11th element in the periodic table. Well, who could tell me how many protons are in sodium 20? Not a trick question. The answer is 11. Absolutely. Absolutely. Who could tell me how many neutrons are in sodium 11, or sodium 20 rather? Yeah, there's 9 because 9 plus 11 gives you 20. And electrons, there must be 11 because there's no charge. All right, if we do sodium 22, it's going to have 11 protons. It's going to have 11 neutrons. And it's going to have 11 electrons. Now notice this one here, it just says oxygen 17, but it doesn't tell us the atomic number. Could anybody tell me where I would go to find the atomic number? Where would I go to find the atomic number of oxygen? Exactly, I would walk over to the periodic table. And on the periodic table, oxygen is element number 8. So I don't even need a periodic table, or sorry, I don't even need to have that written. I know that oxygen is always going to have 8 protons. If the mass number is 17, what plus 8 gives me 17? The answer is 9, and the number of electrons is going to be 8. All right. For carbon 14, we got 6 protons, we got 8 neutrons, and we've got 8 electrons. All right, well, let's move on from there, and let's take a look at the modern periodic table. There's some very interesting history with respect to the periodic table, but I'm going to have to skip that history in the interest of time and just kind of show you around the periodic table. You'll notice that the elements are organized according to their atomic number, but they're not just laid out in a rectangle, are they? Kind of laid out in a little funky way, and there's a good reason for that. And as we progress through Chemistry 111, it will become more and more clear why the periodic table is in fact organized the way it is. Well, we're going to start with the horizontal rows of elements. If we have a horizontal row like this or like this, those are called the periods in the periodic table. Okay? If you think about the word period or periodic, what does it mean? It means something that's going to happen again and again and again. And what you find in the periodic table is that the elements are arranged in such a way that we see commonalities in terms of their reactivity and their physical properties and mostly their reactive properties. But we see these properties repeating over and over. So periods are the horizontal groupings. If we look at the vertical, okay, the vertical groups like this, these are called groups. So period, horizontal, groups are vertical. Now the groups are numbered. We have group 1A, we have group 1A here, and then we have group 2A here, then we have group 3A, 4A, 5A, 6A, 7A, and 8A over here. We'll talk more about that as the course progresses. Now you also see just the Arabic numbering, 1, 2, 3, 4, 5, 6, 7, all the way to 18. Now it depends on the situation which one of those we will use. But before we get into that, a couple more things. You need to know that the periodic table is divided up kind of in 3 major sections. The far left side of the periodic table, and in fact, the vast majority of the periodic table, is everything that's in green here. Oops, I didn't mean to include that. Everything that's in green here, everything that's in green is a metal. Everything that's in green is a metal. So you can see that most of the periodic table is in fact metals. Anything that's in blue here, these are non-metals, and anything that's in purple here, these are metalloids, what are called metalloids. Now, if you're thinking that they must be kind of in between metals and non-metals, well, I'd say there's some truth to that, but I'd say metalloids, it's kind of like they react like metals some of the time and they act like non-metals other times, depending on the situation. There are some groups in the periodic table that are of great interest to us in General Chemistry 1. Those groups are group 1A, 2A, 7A, and 8A. Group 1A is called the alkali metals. Group 2 is called the alkaline earths. In fact, that's a spelling mistake. This one is not alkali, it should be alkaline earths. Anyhow, alkaline earths. Group 7A is what we call the halogens, and group 8A is what we call the noble gases. It just says noble gas, anyhow, noble gases. And we are going to, the reason, if you're like, why do those groups have names, and the rest don't? Well, some of them do. For example, and this is something you don't need to know, but if you look at these three elements here, you have copper, silver, and gold all in one place. Sometimes we call these the coinage metals, and that's never going to come up in this class. But just so you're aware, there are other group names, but these four that I have highlighted in orange are the most important: the alkali metals, the alkaline earths, the halogens, and the noble gases. They're going to come up a lot in this class. Well, let's switch gears again. I'm going to skip this slide and move right on to molecules, because molecules are of paramount importance in Chemistry 111. It says a molecule is an aggregate of two or more atoms in a definite arrangement held together by chemical forces. We even saw some examples of molecules already this evening, things like carbon dioxide or carbon monoxide or water. These are molecules that you probably have heard about even on the news. We talk about water and carbon monoxide and carbon dioxide. But the definition stands that we have two or more atoms bound together by chemical forces. Well, something that you might not know if you've never studied chemistry before is that you can have a molecule that is made out of two atoms that are identical. Well, yes, you can. Okay, if we have two nitrogen atoms bound together, for example, N2, that is considered a molecule. If we have two hydrogens or two oxygens, those are considered molecules. Why? Because they are two atoms held together in a definite arrangement by chemical forces, right? They fit the definition of a molecule. Now, this is a mistake here. It should be B lowercase r2. But anyhow, a diatomic molecule is any molecule that contains only two atoms. You saw that I looked at, or I showed you carbon monoxide already. CO, only two elements. HCl is another example of a molecule that consists of only two atoms, so diatomic molecules. And as you can guess, a polyatomic molecule is any molecule that contains more than two atoms. We have some great examples here. O3, that's ozone. I'm sure you've all heard of the ozone layer. The next one, water, you probably know that. NH3, can anybody identify NH3? Has anybody been reading ahead, getting ahead in the class? Yeah, it's ammonia. Absolutely. NH3 is ammonia. Yeah. And CH4 is methane. It's one of the major components of natural gas. Anyhow, molecules. Well, let's move on from there and let's talk about ions. I referred to ions earlier on, and I said that an ion is an atom or a molecule that has a charge, but I didn't really qualify what if the ion has a positive charge or what if the ion has a negative charge. If an ion has a positive charge, we call that a cation. Call that a cation. The way that I remember that is C-A-T-I-O-N, right? The T kind of looks like a plus sign, so a cation. Whereas an anion has a negative charge, and the way I remember that is anion, right? If you circle the A, it has a cross piece in it that kind of looks like a minus, so anion and cation. Now, if you're wondering, well, how would I get an atom or a molecule with a charge? Well, it's going to be based on gain or loss of electrons. Why would that be? Because, and if you're like, well, why can't I shift the number of protons around? Because if you change the number of protons, then you have a new element. And we're not talking about nuclear chemistry. That's something that's covered in general chemistry too. And it's only a small section of that class. So again, if I have a cation, if I want something to have a positive charge, let's start by looking at a sodium atom. If you go over to the periodic table and you look at sodium, Na, it's element 11. That means it's got 11 protons. Sodium has no charge by itself. So that means that it must have 11 electrons to balance that out. If we want to make a sodium cation, however, a sodium with a positive charge, it's going to have to lose one electron. Why? Because electrons are negative. If you take something positive and you remove a negative from it, what are you going to get? Or sorry, if you take something and you remove a negative from it, you're going to end up with, you remove an electron which has a negative charge, you remove a negative charge, it's going to become more positive. That's what I was trying to say. So we go from something that has 11 positive charges, 11 negative charges. Now we end up with something that still has 11 positive charges, but it's only got 10 negative charges. So if you take 11 and you add -10, you get +1. Okay, that's where I was trying to get to in my mind. Anyhow, in terms of an anion, if you think about chlorine, we look at chlorine. Chlorine is element number 17 on the periodic table. It's got 17 protons and 17 electrons, 17 positive charges and 17 negative charges. If I want to have a chloride, which is basically just a chlorine with a negative charge, so it's a chlorine anion, I'm going to have to add an electron, because if I have 18 negative charges and 17 positive charges, well, if I take +17 plus -18, I get -1. All right, there we go. So a cation and an anion. All right, types of ions. I can have either a monatomic ion, which contains only one type of atom, or I can have a polyatomic ion, which contains more than one type of atom. The polyatomic ions that you see here, you have to know the names of these polyatomic ions. All right, in the interest of time, since we only have 5 minutes remaining, I'm going to look over the remainder of the slides with you, and just to let you or make you aware of what you need to know. Again, it's a lot of material, but we missed a day because of the snow day. And so you're going to be responsible for watching the videos, again, that I have posted on D2L, and I also sent them out in an email. They're just recordings of my lecture from last semester from the exact same class, exact same content. I wasn't nearly as rushed because we didn't have a snow day. But let's take a quick peek here. Ions on the periodic table. I cover that in my lecture. Formulas, models, types of formulas, molecular formulas, empirical formulas. I go over what's called an ionic compound. So those are held together by electrostatic forces. Talk about what's a reactive element. I talk about how to make formulas for ionic compounds. We look at making formulas for ionic compounds, and then nomenclature. You'll notice that I posted an entire video series to D2L about nomenclature. Nomenclature is the biggest part of chapter 2. It takes a long time to master it, so I recommend making flashcards or something like that to help you master nomenclature. I talk about how to name ionic compounds. I talk about how to name polyatomic ions, which are found on this slide. The more polyatomic ions are found here. You have to know how to name ionic compounds like the ones shown here. You have to know how to derive formulas from the names. Then we talk about molecular compounds, which are made of only metals and nonmetals, just nonmetals or nonmetals and metalloids. So this is all covalent compounds, covalent nomenclature, a flow chart. Then we talk about how to name an acid, how to, the acids that you need to know, oxoacids, oxyacids, oxoanions, naming oxoanions. There's some examples here. Bases, we talk about bases and hydrates. Go over that. Common names of compounds. You don't have to have all these memorized. Really, the only common names you need to know are water, ammonia, and that's about it, really. Organic chemistry, I probably won't ask you anything about organic chemistry, and that's it. So that's all the content that you have to have for exam 1. So again, during our next lecture, I'm going to go over the practice exam. Where are my students? Come on, I can't see you at all. There we go. Again, I repeat myself. I know it's a lot of content for you to go over in the videos, but again, just due to the snow day, we got behind quite a bit in terms of lecture material. So again, I implore you to watch those videos more than once. You have a lot of time before the exam. It's not until February 2nd and 3rd, so that's quite a bit of time to study. It's only 2 chapters. Look over the practice problems. I have all the solutions posted to D2L. The last thing is for the people who are in group 1 that didn't make it to lab, we're going to have to stick to the same schedule, and I'm going to have to ask you to complete the first day lab tasks sheet, which I don't think is posted to D2L. I'm not sure if I did post it there. Anyhow, in the interest of time, because we're almost out of time, I'll tell you what, if you are in group 1, I'm going to send you an email in the next day or two. Oh, you saw it on there? Good. Okay, it's on there. Either way, Warren, for anybody who's in group 1, I'm going to send you an email anyway, and just to really make sure that you know what you have to have done for our first lab meeting where we do our first official lab. Okay. So I will prepare a video about that, just so you're not lost. Either a video or just an announcement or something, just so you know. I'll put like 1, 2, 3. This is what you got to have done when you come here. And then everybody who's in group 2, well, I'm going to meet you on Tuesday. So after we do the practice exam, we'll meet. Okay. So personally, I'm not an instructor that likes to rely on videos a ton.